Hi guys, it's Miss Simon. So I wanted to make this video today to help you guys out with science. So remember, yesterday you watched an Edpuzzle and kind of reviewed what net force is. So before spring break, we started talking about forces. And we know that there are things that we call contact forces and things that we call distant forces. Remember, we've been learning about contact forces. And remember, our three types of contact forces. If it's a contact force, it has to be touching the other object. Our three types of contact forces that we learned about were, remember, applied force, friction, and normal force. So now what we're going to do is get into those three other types of forces that we call distant forces. Remember, distant forces, they don't have to touch each other. They're not in contact with one another. So let me share my screen here. And remember, if I highlight it, make sure you put it down in your notes. All right, so in our notes, please, non-contact forces, non-contact forces. Remember, if a force is non-contact, that means it's not touching one another. And here we can see our three types of non-contact forces, okay? Well, we see here we have magnets. We have you ever been shocked when touching a doorknob? And finally, our last non-contact force is why does an apple fall to the ground when they let go of it, even though nothing is touching it? What force is that? I'm sure you can think of what force it is when an apple falls to the ground. So again, these three that we're going to review are all non-contact. Nothing's touching it in order for it to happen. Another name for non-contact forces are distant forces. So as it turns out, a force is not just a push or a pull. Objects can apply a force to one another without actually touching it. Things do not have to touch to cause a change in motion. These are known as distant or non-contact forces. So go ahead and put this down. Things do not have to touch to cause a change in motion. These are known as non-contact forces. And let's see if we can remember what are those three non-contact forces. We briefly talked about them before spring break and they were on the previous slide. All right, moving on. Electrical, magnetic, and gravitational forces are all example of distant forces. Okay, so electrical, magnetic, and gravity, those are your three distant forces. Go ahead and put those down, please. Electrical, magnetic, and gravitational. And all of them, again, they're all distant because they're not actually touching one another. And we can see here this example, we see, I'm sure you guys as well, have gone down a slide and your hair stands up. That's due to electrical force. Or on the previous slide, we saw about when you touch a doorknob and it electrocutes you. Okay, that's an electrical force. You're not actually touching the electric, okay, but you still get a force from it. Magnetic, okay, when something is magnetic, it attracts to something else. Okay, those two things are not touching each other to be pulled by the magnet. And finally, gravity, okay? When this little girl is running, all of a sudden she falls. That force of gravity, what pulls that apple down to the ground, even though nobody's pulling it? Gravity. So our three distant forces, again, are electrical, magnetic, and gravity. All right, moving on. So the first one we're going to talk about and focus on today is that of magnetic force. So magnets are any object that tends to push or pull on one another and certain other objects. So go ahead and put this down in our notes, please. A magnet, magnetic force, any object that tends to push or pull on one another and certain other objects. So again, magnets are things that they pull on other objects, okay, when they enter their magnetic field and they pull them and they stick to them, okay? They pull them, but they're not actually touching them, but they get pulled by the magnet. So do magnets attract all objects? Well, if we think about that, no, we know magnets do not attract all objects. Okay, for example, I have these two magnets here. Okay, if I had a paper clip, okay, as I get it closer, it pulls into that paper clip. Right, and we can see that. Okay, so obviously it's going to attract something that is metal, but this metal, this magnet, is not going to be pulling this pencil. Okay, if I let go of this pencil, it's just going to fall. Okay, it's not attracted to the magnet at all. So no, not everything is attracted to magnets. And this is an example of what we look at with a magnet. Okay, it's called a horseshoe magnet and it's shaped like a U. Now, a magnetic field is an area in which a magnet can apply a push or a pull without touching the magnetic object. Okay, so it's the area around a particular magnet that can pull an object in without touching it. Okay, so go ahead and please put this in our notes, please. Magnetic field. A magnetic field in the area in which a magnet can apply a push or pull without touching the magnetic object, and magnetic objects in a magnetic field can be attracted or repelled by the magnet. So a magnetic field is the area around this that can attract or repel something, okay? And we'll go through what those mean. So if something is attracted to it, it means it's pulled to it. For example, this paperclip is attracted to the magnet, okay? They're attracted to the magnet. When it's repelled, it means it's pushing it away. And magnetic fields are represented by drawn lines around it so we can understand how they affect each other. So if we look at this picture, we see the arrows that tells us how the magnetic field is moving, okay, and the direction of the magnetic field. But we don't ever see these magnetic field lines, okay? Because if we look at like a magnet like this, I don't see lines coming off of it, okay? So magnetic field lines are always there, but they're invisible. We do not see them. So of course, we never see those lines. However, covering a magnet with a piece of paper and sprinkling metal fillings on top of it reveals those lines. We don't see them, but we can make them appear. So I'm gonna actually include a video for you guys. Also, in addition to this Edpuzzle, so you can see what those magnetic field lines look like. So you might also notice that magnets don't work if they're far from another magnetic field. The farther an object is from the center of a magnetic field, the weaker the force it feels from the field. So if we look at an example of this, okay, if we look at this picture, obviously these nails that are closer to the magnetic field are going to be pulled in because it's a greater force because it's closer. These nails over here are not going to be pulled in because it's farther away. So it has a weaker force. So go ahead and put this down, please. The farther an object is from the center of the magnetic field, the weaker the force it feels from the field. And that makes sense. The farther away it is, less chance it's going to be attracted to the magnet because the force is weaker. All right, moving on. Now let's look at the polarity of magnets. So all magnets have a north pole and a south pole, just like the Earth has a north pole and a south pole. Magnets have a north and south pole. The magnetic field goes from the north pole to the south pole. This is why the poles repel each other and opposite poles attract each other. Okay, so it's very important. Magnetic field goes from the north pole to the south pole. This is why like poles repel each other and opposite poles attract each other. So the north always wants to find a south. Okay, so if it's a north end of a magnet and south end of a magnet, they're going to attract each other. They're going to pull each other in. A north always wants to find a south. But if the poles are alike, they're going to repel, which means they're not going to stick together. Okay, they're gonna go away from each other. So in this example here, we see repelling forces, the north and the north. Okay, we see these magnetic field lines, they're not connecting, they're pushing away. So like poles repel and push away from each other, unlike poles attract each other and connect to one another. So a north is going to go with the south is going to go with the north, but a north will never go with the north, and a south will never go with the south. So basically what this means, guys, is Earth itself is actually one giant magnet. It has its own magnetic field. So like I said, we have a North Pole and we have a South Pole, and the North is always going to try to be getting to the South. That's why our Earth continues to rotate on its axis, because it's always trying to find a South, because it's attracted, the North is attracted to the South. And we can see that in this picture. Okay, so again, our Earth is actually one giant magnet. Which of the following is not true about magnetic force? Magnetic fields are the area around a magnet that can push or pull another magnetic object. Opposite poles attract one another. Magnetic forces flow from the North Pole to the South Pole. Or like magnetic poles attract one another. Which of those is not true? If you said D, like magnetic poles attract one another, you are correct. Remember, like poles push away from each other. They repel each other. Unlike poles attract each other. Which location would experience the greatest magnetic force? Location 5, location 3, location 1, or all of them are the same? If you said location 1, you are correct, okay? And this is why, guys. Let's take this magnet and this paperclip, for example, okay? If I have it all the way out here, okay, it's not going to be pulled by any type of magnetic force. It's too far away. The magnetic force is too weak. But as I get closer to the magnet, about right here, it pulls it in. Okay, so that location 1 is going to have that greatest magnetic force. All right, guys, so that is it for today. Okay, so I hope this video was helpful, and I'll see you guys later. Bye.